Okay, so we kind of ended around this picture comparing operating systems to web browsers. And what we were saying is that operating systems have certain primitive things they work with. System calls are the operations that they have to protect. Processes are sort of the unit of protection. They're trying to protect one process from another. What goes on within a process, operating systems don't worry about. It's up to programs to worry about that. And then we have stored data on disks through file systems. The principles that we put onto access control lists are users, so that we think about when sharing data, which users can talk to which other users, and the vulnerabilities we're looking at are root exploits that let you compromise the kernel and take over the whole machine, or buffer overflows that might let you take over the process that's running. So in a browser, the primitives that we have are this document object model, which is sort of the data structure representing the web page that's being rendered, or the set of web pages. We have containers within that are frames that can be generated from different sources. So frames, in a way, can be a bit like processes. And for persistent storage, we have cookies that are stored locally that might have secret information that we want to protect to make sure that only the right web pages can see the right cookies. A question that comes up is, what do we consider a principal? So if a frame is like a process, what is the correspondence with a user? And we'll talk about what's called the same origin policy in a little bit. And then when we look at vulnerabilities, we have a different set of vulnerabilities. So we certainly worry about things like buffer overflow attacks, because if you can overflow a buffer in your browser, you can do anything as the user. You can see anything that the other web pages are doing. So we worry about that, and people write browsers to defend against that. But we also worry about malicious web pages. So we worry about web pages where one website is trying to compromise another website through the browser, through cross-site scripting, cross-site request forgery. We also look at vulnerabilities that might look at your cached history to disclose something or to compromise you. So the thing to think about is, if you look at a browser, there's a lot of different things going on here. So up at the top, you see there's a couple of different tabs that are open. And so each of these tabs is a little different. We then have a window. And we're going to give a JavaScript context to sort of each different piece of context. So we're going to give a JavaScript context to this whole tab, which means that there's some JavaScript running that controls this tab. We're going to have another context for this frame, for this window of what's being displayed, because it might be from a different source or be related to something different than the tab itself. And then on this, we might also have another frame, which is an ad, where the content and the scripts for this ad are provided by an ad company, not by ESPN. So we want to have a context for this ad. And the idea is that each of these contexts kind of get to see different things. They get to have different permissions as to what they can do, what information they can access, what cookies they can read, where they can connect on the network. And they have different rules about what they can display on the screen. So what the browser has to do is sort of keep these things separate and figure out, in each case, what is that JavaScript context allowed to do. So we think about, what is it that scripts might do that we need to control? So this is sort of in our access control matrix. We had to think about what were the set of objects or actions that code could take that we want to secure. So these are the things that scripts can do that we want to worry about. And it's not an exhaustive list, but it gives you a sense. So one is, a script might want to contact a web server. For example, scripts on your Gmail web page want to make calls to Google to retrieve your mail. Scripts on other pages might want to contact a ad company to retrieve a video to display, or to respond to something you click on. Another thing a script might want to do is to access cookies. So cookies are stored information. They can store information about your username, your password, some kind of identifier that identifies what kind of user you are. So scripts might want to use this so that they know how to personalize the website for you. And then scripts also want to read and write this document object model. So the way that a script sort of makes your website interact is it's going to change the document object model, which will change what gets displayed on the screen. So to actually respond when you mouse over something and it sort of pops up a little window, JavaScript is going to sort of change the DOM, and when you mouse over it, it's going to change what gets displayed to sort of show that content. So these are all things that scripts want to do. And what the browser has to do is decide, should this be allowed? And so this is actually one of the biggest problems that browser vendors had for a long time, was figuring out what is the right policy. It wasn't about how to build an access control mechanism. It was, how do you even know if a web page should do something? So any thoughts on why this is a hard problem? I mean, it seems like it should be pretty easy to sort of think about what a web page should access. It should access its own content, nobody else's content. Any thoughts on why this took sort of 3 or 4 or 5 years to figure out? Yes. Okay, so a major thing that browsers do to be more flexible is to allow plugins. And so plugins aren't written in HTML, and so figuring out a policy that both covers your web pages that are in HTML and JavaScript and is secure when you have extensions that might be written in C or some other language, and still provides protection can be very complicated. It's a good point. Other things that might make this hard. Yeah.
There are so many users, so you have to verify who is requesting what.
Okay, so in this case, there's two kinds of users. There's you as a user of a web browser, but there's also so many web pages out there that want to do lots of different things. And so one of the challenges in coming up with policies is figuring out, if I have a new policy, how many web pages will it break and do I care? Right? So if you come with a new policy and it breaks Facebook, you have 1.5 billion people who care and are going to complain. If you break my web page, then I'm the only person who cares, and I might complain, but nobody else will complain. And so creating new policies should sort of work for, you don't want to break the whole internet when you create a new policy. So finding policies that make things more secure without breaking everything is very difficult. Other thoughts on why creating policies might be hard? Thinking about topics we've covered so far. So I'll give you the answer. Thinking like a security person, the problem is that it's hard to know what is safe until you see an exploit. So you might have thought before you took this class that using stir copy and allocating local variables was safe. But now that you know about buffer overflows, you know that that's unsafe and we need a policy to prevent it. Similarly, if you design a policy saying, oh, I'm going to let web pages access, I'm going to let content that you embed access the outer page so they can pull your username conveniently, that might sound fine until somebody exploits it and you realize that your whole system is insecure. And so the challenge is that it's very hard until you see a lot of exploits and attacks to know what policy you need to defend against those. And so there's a general rule that a lot of policies are sort of driven by attacks, as compared to like people sitting in a room and being smart and thinking about this is the right policy. It's a lot of let's sort of see what people have done and how do we break the common attacks we know about, because it's so hard to sort of imagine what attacks are. I was listening to a podcast and it generally said that pretty much everybody is smart enough to design a security mechanism that they can't think how to break it. That doesn't mean you're smart enough to design a security mechanism that nobody can break it. And so web policies sort of have that flavor. If people design things smart enough that they couldn't imagine how to break it, but when you have a billion people trying to break it, you get a lot more sophisticated attacks. So the things we want to think about are, if you have two tabs open in your browser, or two windows, and they're both from the same company, say they're both Amazon.com, should the JavaScript on one page be able to access the content from the same company on the other page? So could one browser window cause the other browser window to do something, or could it read content off that? So what do you think? Should that be allowed or not allowed? So one way to think about this kind of problem is, if we disallow it, does it make a difference? So what you could say is, if I have two web pages open by Amazon, Amazon created the code that runs on that, they can communicate with Amazon servers. So one web page could upload everything on that web page to the Amazon server, And then the other web page could periodically pull a server to Amazon and download all that content. And that's totally under Amazon's control. And so even if I don't allow communication between those two web pages from Amazon, Amazon can do that itself. And because Amazon can do that itself, there's not a good reason for me to block it, because it won't be an effective security mechanism. And so in that sense, I might as well allow those pages to communicate. So if I add something to my shopping cart on one browser page, my shopping cart on the other browser page can be updated to say there's something in it, which is very useful. So what about when requests are to the same website? I think that sort of follows that we can think that there are cases where it is useful when you're talking to the same website or web particular page that we want to have some communication between them. So the way this works is that you have some JavaScript context. So this is the actual running JavaScript code for some visual element. We talked about the tab, the window, a frame, and this context is going to want to do some things. Yes?
Quick question about sharing data between two different web pages by the same company. So for a large company like Amazon, and you find a vulnerability in your local server, and you're trying to log in from, you're trying to exploit a more secure server, like, I don't know, Amazon's headquarters, would you be able to then dork with the more secure server if you're able to have two different web pages from your local unsecured server to the...
So that is an excellent question, which we'll get to, which is what does it mean to be from the same place? Another problem that comes up, which is, suppose there's two websites on WordPress. You have a website on WordPress, I have a website on WordPress. So WordPress is the company. Should your website be able to mess around with my website because they're both from WordPress? And so that argues that we don't necessarily want to say the same company can see everything from it, because some of those web pages might actually be user content and not coming from the company itself. So that's a reason that we might want to say, well, really, it's the same website, which is a machine name with some path attached to it. It might be we want a particular web page, which would be more or less the same complete URL. So you're exactly right that much as I said in this Amazon case it's safe, it doesn't mean that's always what's safe. Okay, so for DOM access control, we have this JavaScript context. It wants to do something. So what we have is what's called the DOM reference monitor. And you might remember we talked about reference monitors about 3 weeks ago. The idea is the reference monitor is the piece of code in the system that checks all access to see if it's correct. This is a concept that's used in operating systems. So in operating systems, the reference monitor is the piece of code that will evaluate access control lists in the file system. In the browser, it's part of the browser that will check to see, are you allowed to access this part of this particular object? So what the DOM reference monitor has to do is evaluate, is this context allowed to access this object? So an access control decision. And if it is allowed, it will grant a reference to that object so the JavaScript context can now actually communicate with that object and manipulate it in some way. So one thing to note is once you control an object reference, it's a bit like a capability, because you can manipulate an object, you can now pass it to someone else. So we have an access control list in a way in the reference monitor, but then capabilities in these references. So this means that if I am controlling an outer window and I have some frame inside of it with some content, I can reference an object because I'm allowed to and give it to that piece of content inside there to reference that object if I want to let it. But I get to make that decision, hopefully, as that outer piece. So one thing to note is it's very important to think about who controls the code running in a context. So suppose you have a web page and for some reason you let me put some script on your web page, right? Suppose I have some gadget and I say, if you want to use this gadget, just embed this little script piece of HTML into your web page. I am now controlling some code in your web page, and that script that you put in there, which probably you don't understand, at least I never understand it, can now do anything your web page can do, read its cookies, things like that. So this means that if you have script on a web page, you can hand it off to someone else and grant them access as well. So the basic policy that browsers have adopted is what's called the same origin policy. And what it says is that every web page has some origin. And the origin of a web page includes the protocol, whether it's HTTP for unsecure HTTP, HTTPS for secure HTTP, a host name, Amazon.com, aws.amazon.com, research.cs.wis.edu, and a port number, port 80, port 8080, port 8000, something like that. And then the rule is that scripts in a frame can access its own origin. So it can access cookies that are related to that origin. It can access DOM objects that are from that origin. So if there's other elements elsewhere on the screen that are sibling page, if you have two tabs open or you have two frames that are from the same origin, then one frame can access the other. And so again, the idea is that because the origin controls this, the origin, that website could pass information through the website, we might as well let you pass information directly through the browser. But the flip side is that a frame can't access things from other origin. So if I embed a gadget from Google on my web page, it can't read other things on my web page because its origin is google.com and my origin is research.cs.wis.edu. So to get to your question, this means that if you trust, HTTPS, if you have one web page that is https://www.amazon.com, content on that page can't access something at aws.amazon.com because it has a different domain name. So if we look at sort of how these frame relationships work, so we also want to think about when you're drawing things on a screen, who should have control over different elements. So what we were talking about before was just DOM objects and not the visual layout of the screen. So in the screen, we have a series of frames, and each frame has sort of content from a different website or different URL. And the relationships we have is we have a child relationship where one frame is embedded inside another frame. Which means we also have a sibling relationship. So this is the case where we have two frames that have the same parent frame. We also have a descendant relationship, which says that, if you go through child relationships from some frame to some other frame, then you eventually find the other frame. So this is, grandchildren, great-grandchildren, great-great-great-grandchildren. And the reason I bring this up is we want to think about, in these relationships, at what point, who should get to read whose data and access whose data. So we had one policy, which was the same origin policy, but we might want other policies that talk about embedding things and who gets to read things that are embedded. Any questions? There is an ancestor opposite of a descendant. Okay, so what we want to think about is what should the policy be? And the things that we're trying to look at for browsers is two things that we can do. one is can script. Can one frame script another frame? Which means can you access its DOM objects or sort of program the elements that it's doing, that sort of change the elements, change what it's displaying. If you can script a frame, you can change what it shows on the screen. The second one is can navigate. And navigate says, can you change the origin or the URL in some other frame? So can navigate says, I can choose I can take this frame on your screen and I can make it change to some other web page. Can script says, I can take a frame on your screen and I can change what it's displaying and look at the data inside of it. So in these relationships, which I showed before was sort of child, descendants, siblings, how do we decide who should get to script and navigate other pages? So there's a couple of options people have come up with. So as you can guess, the early browsers were just permissive. They said anything on your screen can, any part of your web page can cause any other part of your web page to be navigated someplace else. And any part of your web page can view all the data and the DOM from any other part of your web page of what's being displayed. So as you can guess, this is terrible because you embed some content and it can read everything. So we don't like this. And the reason we particularly don't like it is things like ads, right? Every web page has a ton of ads. Those are in little frames. Do we want that piece of ad that we're running, that we have on our web page, to see everything else that we're doing? We don't know where that came from. We don't necessarily know if it was connected over a secure socket or not. So we think that's bad. So some other policies are child. This says that if you're the parent of a frame, you can cause the child frame to do something, and that's the only person, the only frame that can cause, the only relationship that allows you to navigate another frame. If there's a subframe inside the child, you can't control that. Descendant says that you can cause any, if there's a frame, you can cause that frame to do something, as well as any frames embedded inside of that. So it's sort of a transitive relationship there. So how do we think about these policies? How do we sort of evaluate? I think we can easily say, in this class, anything that says permissive, we're going to rule out as being bad because nothing should ever be permissive. So that is bad. But of these other two, child is a little tighter because you can only navigate a frame through the direct parent. Descendant is a little looser because you can navigate other things inside of it. So if you embed an ad, that would say if I embed an ad, I can change that box where the ad is being shown. And if the ad embedded something, I could also change what that ad was showing me. So any thoughts? How would you reason about this? So a lot of times, as I've sort of tried to show you, the way we think about this is to think, is there some other way, is there something else you can do that achieves the same purpose that means there's no reason to block certain things from happening? So as a parent window or a parent frame on your screen, is there something you can do that gives you the same power as navigating a frame or a subframe? Yes.
Well, if we have the ability to manipulate the DOM, then can't we just change the source, which is negative?
Well, so that's the question is that we don't, what we're talking about is, do you have the ability to change the DOM?
Oh.
And so we're trying to decide, should you have that ability to change the source or not? But you're on the right track. Other thoughts? Yes.
Well, if you are the parent and you want to modify the child, can you tell the child that you modify its child?
You could try to tell the child to modify its child. That's true. You could modify the child and cause it. The thing is we're talking about specifically navigation. So you can navigate the child someplace else. But if the child doesn't have some control that lets you, through the URL, change that grandchild, you can't directly make that child display something it wasn't coded to do to begin with. So the child web page the child content has some limits on what it normally will display. So a good way to think about this is to say, well, we have this box on our screen where the parent is running. Inside that is some box where the child is running, and inside that is some box where the grandchild is running. Right? This whole screen here was sort of designed or owned by the parent. So the parent at any time could say, I really just want to go like this and show nothing and remove the child altogether. So we have nothing here. The parent could then decide to display something else here instead. Or it could display, for example, some kind of image. And then some other child on top of that image. So the general thinking here is that if a frame controls some pixels on the screen, then the frame should control any subframes that are drawing to those pixels on the screen. Because the frame can draw whatever it wants there. It could download a bitmap of what this page looks like and draw it so it looks just like the real content. It could embed its own code that sort of draws this thing. So the idea is we're going to trust the parent with this rectangle, so whatever happens inside this rectangle, we're going to trust the parent for. So it can control, we let it control the child and the grandchild. Assuming the child we're giving this box here, so we're going to trust it with everything inside this box. Because it can already on its own decide not to display the grandchild, display some other grandchild. So this is a nice way to think about when should we trust something. If we delegated some piece of screen for you to draw on, then you get complete control over what you show on that screen, and you can sort of navigate the things inside of it because you chose to include them. If we don't like what you're doing, then we can decide not to show the child anymore. So here's sort of an example now of why we don't like permissive. So this was an old site that Google had where you could have ads on the main page. And there's a problem with permissive. This ad you were showing, because it was permissive, could see the whole DOM. So when you entered your password, it could then read your username and password. Or it could potentially put up a fake login screen here that would overwrite the normal login screen and cause you to enter your username and password so that it would go to the evil site, not the regular site. See, this is sort of the fake login there. So this is the policy that people come up with, and this becomes the, sorry, I jumped ahead a little bit, that becomes the descendant policy. Because the way the frames are aligned on your screen says that every child has to be within its parent, so all of the descendants from a frame are sort of embedded within that frame. So this means that we end up with sort of two rules. One is that you can control all your descendants, and the other is the same origin rule. And so it says that you can control a sibling if you have the same origin, or you can control your descendants that are within your frame. So this means as a web page designer, it sort of says if I want to isolate things and keep them separate, I should put them in different frames, and I can have my sort of evil content here and my safe content here, and I should can have some content that my evil content can't see anything that's going on in this outer frame or in this other frame over here. Okay? So we're now going to move on to cookies, how cookies are used, and some vulnerabilities that cookies have. So cookies were added in early browsers because in early browser there was no way for the browser to remember anything about who you were. Every time you went to a website, all it knew was that somebody was connecting over the internet, but it had no information about you. And what it meant is that you had to encode in the URL anything you wanted to pass along. So if you wanted to remember, for example, that somebody was creating a shopping cart, you had to embed something in the URL that said this is the shopping cart they're using. There was no way to have it automatically remembered when somebody connected. Or even if somebody logged into the site, there was no way to know when somebody connected again later they were logged into the site. Or from when you go from a login page to something else, the only way to remember that is to put in the URL, here's some information about who's running, who's connected. The idea with cookies is that this is a way that servers can store information on your computer, and then when you connect to the same website later, that information will be provided automatically. So when you first connect to a website and you do a GET request, which is sort of the basic request to fetch information, the website can send back a cookie using the set cookie header, and it can provide information. So it provides the name of the cookie with some value. So it could be, username, password, favorite cookie flavor, something like that. It provides a domain name, and the domain here is going to really says which website should this cookie be for. Should the cookie be for Amazon.com, www.amazon.com, aws.amazon.com? So we're going to scope it to sort of what are the set of websites we want to use this cookie for. We're going to have a path, so we can also say, is this cookie for the whole website, or is it only for particular paths? So like if I want to use cookies on my website at the University of Wisconsin, then I would have the domain be research.or pages.cs.wisc.edu, and the path would be /tilde-swift, because that is my personal homepage, so that would let me see my cookies. Secure says, should you send this cookie whether you're connected insecurely over HTTP or only when you're secure? And then expires says, when does it expire? How long should you keep the cookie around? Because you might want this to be deleted automatically if somebody never comes back to your website, but you do want to remember them, so if they come back somewhat soon, then you see this information. Then finally, there's an HTTP only flag, which says, can scripts access this cookie, or is this cookie only accessible to servers and it's passed along through HTTP? And this will become important as we see later when we think about what malicious scripts can do. Okay, so one thing we think about for cookies is we have to have access control rules. The same way we had access control rules on frames, we need to think about who can access cookies, because cookies have really valuable information, right? When you connect to a website, it's not that you pass your username and password every time. It's that there's a cookie that has some information on it that logs you into that website. So if you can get that cookie, you can impersonate someone to a website and do everything they can do. And we'll see how that works. Okay, so the way the browser interprets this is when you connect to a website, the browser will go through all the cookies that it has for a domain or for some part of the domain. It will find all the cookies that match according to the website you're going to. So if the domain is a prefix of the domain that you're going to, and if the path is a prefix of the path that you're visiting and it's the right protocol, then it will send the cookies automatically. So this is very convenient for websites to sort of, they can control when cookies are shared between their sub-websites or sub-pages, different pages on a website, and what information they put in there. Yes? What? A domain is the host name, www.amazon.com. So we sort of call that part of the URL the domain name. But the reason we do it is because if you sort of, typically the whole thing is a host name. If you strip off the first part, then you often get the domain name. And you might see a case where you might have like 6 web servers, www1, www2, www3, dot something or other. And so this allows you to say, I want to share cookies with the whole domain, which would be Amazon.com, and I don't care which web server we went to, www1, www2, www3. So you can choose sort of that name at the top, that first piece, how much of that has to be the same to pass the cookie along. So now we get to the fun part, which is cookies sound great. Are there any security issues? And of course, given this class, you know they are. So one problem is that cookies have no integrity generally. So there's no checksum that makes sure they haven't been corrupted. When you download a cookie from the website, there's not really a check that it's the same cookie the website sent. Somebody could, inject packets in the network that gives you the wrong cookie. Another thing that can happen is, so the way cookies are stored is you get, for a name and value, you only get to store one cookie. So if there's a username field with some value, you will store one cookie with that name equals value for a domain. So suppose you connect over HTTPS and you get name, the web server saves a cookie, which is, name equals Mike. What happens if I sort of inject some packets to the network and I inject an HTTP packet which is not encrypted and can be manipulated by an attacker that says name equals Bob? What will happen is the browser will overwrite the cookie from the secure connection that said name equals Mike, and it will replace it with the bad cookie name equals Bob that came from the insecure connection. So this means that even though you download cookies over a secure connection, it doesn't mean they can't be replaced by insecure cookies later that will cause you to do the wrong thing. So one question is, why do we care if cookies are insecure? Like, so what if there's an integrity problem and somebody modifies your cookie? Even if they, if they can't read your cookie, is that a problem? Any thoughts on why we might care? Yes.
One of the papers talked about like if you're on Google and I replace your cookie, like my cookie, and I show up my public search history.
So if I replace on Google, if I can steal your cookie on Google, then I can see your search history.
Like if I overwrite your cookie for mine, then you're logged in as me.
Right. Okay. So the example, great example. The example is you overwrite my Google cookie with your cookie. I go and browse the web. I search for how to kill students, how to make pipe bombs, great things. Because I did all this using your cookie, when you go to Google, you will see my entire search history. So you can see everything that I've done because it was done using your cookie or some cookie you control. Similarly, if I send emails without sort of paying a lot of attention, they will be sent as you, which you might not like, but you get to see the emails that I've sent, which means you can eavesdrop on my communication. And so that's why we worry about integrity, because you can make somebody act as a principal that you control, which means you can see what they're doing. Another thing is that you as a browser owner can modify or code on your computer can modify cookies. So you have cookies stored in some file on your computer. You can go in, edit that file, and if the website is not well constructed, you can modify the cookies to do different things. So if you had a website that was sort of saying, did this person pay already, and they happen to put that in a cookie, you could modify the cookie to say, yes, Mike paid already, and when you go to check out, it'll say, great, you paid up already, we'll ship it to you. And so, you have to make sure that as a web server, you have to realize that any cookie you get could be totally fictitious, because there's nothing that ensures that it's actually data you provided. Because either an attacker could have modified it over HTTP, or a user could have modified it somehow before sending it back. Which means you might want to do something on your own. So another example I brought up is this example of WordPress. So if WordPress.com sets a cookie, then and the scope says, if the rule says you just have to match WordPress.com, then anybody else with a domain underneath WordPress, blog.wordpress.com, swift.wordpress.com, can see that cookie. So if you let somebody have sort of user-generated content, they can see cookies if the scoping rules allows it. So again, you have to be careful on web pages that provide user-generated content, that they can sort of see everything. And then, of course, we know that cookies are great for privacy, because cookies are sort of allow web pages to remember who you are and to sort of track everything you do on the internet, which is a whole separate issue, and probably there should be a whole class on that. So any basic questions on cookies? Okay, so what we will do a little bit more detail is to sort of look at what happens with HTTP cookies. So HTTP, remember, is unencrypted traffic, which means that anybody who's on the same network can see it. Anybody who controls a network switch or a router that the traffic goes through can see it, and they can potentially modify it if they work harder. Yes?
How are cookies affected when VPNs are used?
So a VPN is a virtual private network, and what it does is essentially take the data from one side of that network, encrypt it, send it someplace to some other network, decrypt it, and inject the packets into the network. So for example, when I was in Spain, I wanted to watch Hulu, and Hulu wasn't available in Spain. And so I used the VPN back to the CS department, and so my computer would take all of my traffic, encrypt it, send it over the network encrypted to the desktop computer in my office, decrypt it, and then send it out to Hulu. And so what it means is that in the portion where you're not sending the data through that encrypted piece, the same problems exist. In that encrypted piece, all the traffic is encrypted and can't be seen or modified. So either end is still vulnerable, but the middle is secure. Not that I recommend circumventing copyright rules that way, but okay, so let's see first, how do we use cookies for authentication? So you've got some browser, you want to connect to some website. You're going to when you first connect, you're going to send over your username and password. And usually this is done over a secure connection, and you just pass your username and password as they are, unencrypted, unhashed, anything like that. The website will sort of validate, it'll sort of look in the database for your account name. We'll get to that in a little bit. It will then create what's called an authentication cookie, which is some big random number that it can find later. So it can use this cookie to look you up next time you connect and say, oh, I know who this is. It'll then send back this cookie, and it'll say, set this cookie with, it's an authentic with the name off, and here's this big random number. So this random number is now used to identify me. So what that means is that if you know this big random number, you can connect to the website and pretend to be me. So that's why we really don't want to do this over HTTP, which is what is being used here, because that allows anybody to see it. So the next time I connect, I'm going to do it, if I do a GET, the web browser will automatically provide cookies for me. It'll provide this authentication cookie here. The web server can see the cookie and say, oh, I know this is Mike. I'm going to, let him see the flying pigs or whatever it is I want to see. So this is also used for what are called session cookies, which sort of keep track of what's going on just for this session where you're currently logged into a website. So they may not be stored when you close your browser and restart. So in this case, when you connect to a website, you might start with an anonymous session cookie that sort of doesn't record who you are. So this is what the website will set. So this just says this is an anonymous user. We're just going to do anonymous things for them. After we log in, it's going to, if you have to log in every time, it'll set a new session cookie, which actually authenticates as who I am. And the next time I connect, I use the session cookie. So the difference is this is a session cookie, so it's only alive for as long as my browser is open, and then it doesn't get stored. Whereas the authentication cookie before could be stored persistently, and I could, restart the browser next week and still be logged in. So I actually went to my browser and I looked at my GitHub cookies, and you can sort of see this is the host user session same site cookie for GitHub, and it has that nice long string there. And you can see the path is /, which means that any place at GitHub can see this cookie. It can only be used for the same site connection. It's HTTP only, so scripts can't read this cookie. And it lasts for approximately 7 months or so. So what do we do? How do we abuse this? So one way we do is we abuse this with this tool called Firesheep. Firesheep is a tool that you can download and you can run in a coffee shop and use to log into people's accounts. What it does is it sits there and it sniffs for unencrypted packets on the network that have a session cookie. So one of the problems is that people, and it's less of a problem now, but it used to be that people thought encryption was very expensive and they would encrypt the login only. So you would have communication that looked like this. And this piece right here would be HTTPS, and this piece down here would be HTTP. So, in a way this is good. When we're logging in, we have our username and password. So this is encrypted, nobody can see it. When the cookie comes back, nobody can see it. So this exchange is nice and secure. But then when we go to the website to actually do something, read our email, post on Facebook, we are going to provide the same cookie in clear text over the network because we are not encrypting anything. So if somebody can sit there and sniff this, they can just take our session cookie here, and then if they connect to the same website using that cookie, then the website will say, welcome back, Bob. Nice to see you again. So there's a tool that somebody wrote as a Mozilla plugin, and you could just sit there, fire it up on your laptop, sit in a coffee shop, and it would start telling you as it captured the network who you could log in as into which websites. And then you could sit there and click on it, and it would take you to that website as that person. So very easy and convenient to use. So what is the takeaway from this? What do we learn as people who care about security about system design here? Where do we go wrong? Yes?
Complete mediation.
Okay, so how so?
Well, we didn't take care of all paths to get to it.
Right, so we have a problem that we have this sort of secret information that we consider to be secret, and we didn't sort of mediate access to this information. Right, so we said we worried about the password. We sort of treated the password as being the secret information, but we forgot that this session cookie is almost as powerful as the password because it lets you log in. And so we didn't encrypt every single request where this password was used. So what this says is that if you have something that is equivalent to a password, you need to protect it the same way you protect a password. Because if you can use it to do the same things, then people don't need the password anymore. And so just saying we don't want people to see the password is insufficient. So there's a couple things you can do on how to defend against this. One thing we can do is we can try to encrypt the session cookies and see if that helps. So our session cookie, instead of just being a random number we look up can be some secret key that the server knows. We're then going to sort of put the user ID, some expiration time, some other information in the cookie, and then we're going to encrypt the whole cookie this way. What kinds of attacks does this particular approach help us with? Does it help us with anything? So the cookie, the key thing is the cookie is not just a number we look up in a database, but the cookie is now some encrypted data that we have to decrypt on the server, and we can check to see if it's valid. Does this help with the session hijacking that I was just explaining? I see you shake your head. Why not?
Same. I can still send the same information, but just encrypt. So the server still thinks it's me.
Right. So the client can't encrypt this, so the client just treats it as a blob and provides it. So we still have the problem that we have this opaque piece of information that if you get access to, logs you in. So it doesn't prevent somebody from stealing your cookie and using it to log in. So that doesn't work. There are other things that it does. So what about the case where I, as a malicious user, modify my cookie, to sort of say I'm a super user or something like that? Does it help in that case? And the answer is yes, because here the cookie is checkable by the server, so the server can look at this and see, should I be, is it correct or not? So there's actually a real-world case that came up recently. There was a kid's smartwatch being sold in Germany that sort of tracked your kid, and you go to a website and log in, and in your cookie, I think it might have been in your cookie, there was a bit that said is admin. And if you set it to 1, you got to get the administrative access to the user database for all people who'd ever bought this smartwatch, and you could see all the users and track all the kids in Germany who had the smartwatch, which is a totally horrendously bad idea. But it means that, if they had, not that this would be enough, but if they had encrypted it this way, it would at least prevent users from setting that is admin bit to 1 themselves. So it does provide some help. The other thing that you can do is the server, if the user logs out, can record the user logged out, delete the session, which means that when you log out, even if somebody stole that session cookie, they can't use it anymore because it's invalid. A third thing that Google has been proposing is what they call a macaroon. You might have heard of the macaroon as a cookie. So what they do is they encrypt the token the same way, but they put your IP address inside there. And when they get the cookie, they can look at the IP address inside the session cookie, and they can look at the IP address the client is using and see if they're the same. Any thoughts on this as an approach? What does it help with? What does it not help with? Yes.
Help with like could be another computer in the same coffee shop. We'll have a different IP, but now when I take my laptop home, it doesn't recognize me.
Right. So it has the advantage. It does prevent session hijacking when people have different IP addresses, but it doesn't help when you as a user want to move your computer somewhere. It's great for your desktop computer that doesn't change, but if your cell phone moves from cell network to cell network and Wi-Fi networks and gets different IP addresses, then the cookies start to break. So you sort of want to use that in conjunction with something else perhaps to sort of, you know, secure things temporarily while you're connected and then have another mechanism for when you switch networks. Or, you know, the better thing is really always use HTTPS every time you're sending a cookie so you never send anything clear text. So that in conjunction with encrypting the cookies means that clients can't modify their own cookies because they're encrypted, and other people can't see the cookies or modify them because they're extra encrypted when they go over the network.